Welcome to our quantum deep dive. Today, we're plunging into a topic that's, well, not just cutting edge, but really fundamental to how our modern world functions, the future of information transfer. Think about it. Every financial transaction, every scientific breakthrough, even your streaming binge watching, it all relies on data moving efficiently and crucially securely. And with this, exponential growth driven by cloud computing, the Internet of Things, advanced AI, the demand for protected channels against cybercrime, against industrial espionage, it's just never been more pressing. For this deep dive, we've drawn our insights from Yorgos Schneppet's really compelling essay, Quantenkanäle Revolution der Informationsübertragung.
Yeah, and our mission today really is to unpack why our current classical communication systems are starting to show their age. They're hitting these inherent physical and security limits. And then we'll explore how quantum channels aren't just a small step forward, but a truly revolutionary leap. They promise to fundamentally reshape how we ensure both the speed and, importantly, the impenetrable security of our data. We're talking about moving from computationally assumed safety to physically guaranteed security.
It's a massive paradigm shift.
Huge.
So let's start right there at the foundation. What are the fundamental limitations that classical communication systems, despite all their incredible ingenuity and advancements, are currently running into? Where are the real bottlenecks showing up?
Well, classical communication, the kind we use every single day, it's built on Claude Shannon's mid-20th century information theory. It relies on bits, those simple zeros and ones. And this binary nature, it just comes with some inherent physical constraints. For example, whether you're sending data through fiber optics or over wireless networks, you inevitably face signal losses and noise.
Right. Interference and just degradation.
Exactly. Damping effects, external disturbances, they erode the signal. This compromises transmission range and the quality. It's, why your Wi-Fi gets flaky at the edge of your house, or why a long fiber optic cable needs signal boosts along the way.
Okay. So the signal isn't perfect. It degrades.
Yeah.
What other physical limits are we bumping up against?
Precisely. Beyond just signal degradation, we're also constrained by limited bandwidth.
Ah, the spectrum crunch.
Yeah, the available frequency spectrum for electromagnetic waves, it's finite. And as the sheer volume of data we generate continues to just explode, this finite space becomes a massive traffic jam. Think of it like trying to fit too many cars onto a narrow road. Things just slow down.
Makes sense.
And finally, there's latency. In a truly global network, the speed of light itself, combined with the time signal spend being processed at various nodes, routers, switches along the way.
Yeah.
It creates unavoidable delays.
You just can't get there instantly.
You simply can't outrun the speed limit of the universe.
And beyond just the physical limitations of getting the signal from A to B, this is where it gets really interesting, I think, especially for our sensitive data. The critical security risks embedded in these classical methods. It's not just about speed anymore, is it? It's about staying one step ahead of anyone trying to, peek at your information.
Absolutely. The security vulnerabilities are perhaps the most urgent concern right now. Our current classical encryption methods, things like RSA or AES, they're incredibly strong today, but they rely on a single core assumption, that it's computationally too hard for even the most powerful current supercomputers to break their underlying mathematical problems, like factoring huge numbers.
Okay, so it's hard now.
Right. But the looming threat, the big worry, is that future powerful quantum computers could potentially solve these problems. Well, almost trivially, in the blink of an eye, relatively speaking. And that would render our current encryption basically obsolete overnight.
Wow. So something that's virtually impossible for today's best computers could become computationally trivial for a quantum computer. That's a serious vulnerability to consider.
It really is. And another major issue is simply eavesdropping on data streams.
Just listening in.
Exactly. In classical networks, an unauthorized party can often perfectly copy data without disrupting the transmission. This is the basis for man-in-the-middle attacks or just passive surveillance, where someone can listen in on your conversations or data transfers without you ever knowing they were there.
That's sneaky.
Very. And with the growing interconnectedness of our digital world, the increase in cyber threats means communication networks are increasingly attractive targets for malicious actors, everyone from nation-states to organized crime syndicates. These limitations, you see, both physical and security-related, they vividly highlight the urgent need for a new technology, something that radically improves both safety and efficiency. And that's precisely where quantum channels emerge as the potential game changer.
Okay, so if classical systems are hitting these inherent limits, where do we go next? This is where quantum channels step in, promising, as you said, a truly revolutionary leap. How does this new approach fundamentally change the game?
At its core, a quantum channel is a medium designed specifically for transmitting quantum information. And that information is in the form of qubits, or quantum bits. Now, unlike classical bits that are strictly 0 or 1, qubits leverage fundamental quantum mechanical principles. These give them groundbreaking properties. The first one is superposition.
Right. The both at once idea.
Exactly. A qubit can exist as both 0 and 1 simultaneously. This isn't just some theoretical quirk. It's why quantum computers can tackle problems classical ones can't even begin to solve. They perform calculations on many possibilities all at once. Think of it like a coin spinning in the air. It's both heads and tails until it actually lands and you measure it.
And keeping it spinning is key, right?
Yeah, absolutely. That ability to maintain that spinning state, that superposition, for a meaningful amount of time is called quantum coherence. And it's absolutely crucial for building practical systems.
It's incredible to think of information existing in such a fluid state. What's the next big quantum idea that these channels leverage?
That would be entanglement. This is where things get even more counterintuitive, maybe.
Spooky action at a distance.
That's the famous phrase. Two or more qubits become so deeply linked that measuring the state of one instantly influences the state of the other, no matter how far apart they are. Imagine two coins separated by thousands of miles, but if you flip one and it lands heads, you know instantly the other one landed heads too, every single time. It's this perfect correlation.
Yeah.
And this connection, it's absolutely critical for applications like quantum key distribution, or QKD, and also quantum teleportation.
That sounds like something straight out of science fiction. How does this spooky action actually make communication more secure?
That brings us neatly to the no-cloning theorem. This is a fundamental principle in quantum mechanics. It states that it's physically impossible to perfectly copy an unknown quantum state without disturbing it.
You can't just photocopy a qubit.
Precisely. You can't. This is the bedrock of quantum security. If an eavesdropper, let's call her Eve, tries to intercept and copy a qubit, she inevitably alters its delicate quantum state. That alteration makes her presence immediately detectable. It's like trying to, measure the temperature of a single molecule without changing its energy. You just can't do it without interacting and leaving a trace.
So the act of observing changes the outcome?
Fundamentally, yes.
Yeah.
And this theorem is the absolute basis for secure quantum key distribution.
So with these, truly mind-bending properties, superposition, entanglement, and this no-cloning theorem, we're talking about a completely new blueprint for how information moves. Tap-proof communication via quantum cryptography, highly secure data transfer through quantum teleportation, potentially scalable quantum communication networks using quantum repeaters, and ultimately the foundation for nothing less than a quantum internet. It really is a leap from, as you said, computationally assumed security to physically guaranteed security.
Precisely. The laws of physics themselves become your ultimate firewall. It's a profound shift.
Let's talk practical applications then. How do these astonishing quantum principles actually translate into real-world solutions that might impact us?
Okay, one of the most immediate and impactful applications is quantum cryptography, specifically QKD quantum key distribution. Unlike classical encryption, which, as we discussed, relies on the computational difficulty of breaking codes, QKD offers a physically guaranteed solution to communication security. The most well-known protocol here is probably BB84, developed way back by Charles Bennett and Jules Broussard in 1984.
Okay, 1984, that's surprisingly early. And how does this BB84 protocol actually work to secure a key, a message?
Right, so here's a simplified view. Alice, the sender, generates a random sequence of qubits. These are often photons, particles of light. She encodes information onto them using one of two different measurement bases. Think of these like different ways of asking a question, like vertical, horizontal, or diagonal to diagonal.
Okay, two of the different ways to encode or measure.
Exactly. She then sends these qubits to Bob, the receiver, over an optical quantum channel like a fiber optic cable. Bob, who doesn't know which basis Alice used for each qubit, randomly measures each incoming qubit using one of those same two bases. After the transmission, Alice and Bob get on a regular classical channel, could be a phone line, the internet, and they openly compare only the bases they use for each qubit, not the results, just the bases.
Just the type of question they ask, not the answer.
Precisely. And they discard any qubits where their chosen bases didn't match.
And that's where the security comes in, because of that no-cloning theorem, right? If someone was listening.
Exactly. Only the qubits, where both Alice and Bob happen to choose the same measurement basis, are used to generate their shared secret key. The crucial part is this. Any attempt by an eavesdropper our Eve, to intercept and measure these qubits will inevitably disturb their fragile quantum state. Why? Because she doesn't know the basis Alice used either, so she has to guess. This disturbance increases the error rate in the qubits Bob receives compared to what Alice sent. When Alice and Bob compare a sample of their key bits, they'll see these errors and know someone was listening.
So Eve's attempt to measure reveals her presence. It's not just hard to crack, it's physically impossible to eavesdrop without immediately tipping off the communicators.
That's the power of it. Physical law, not computational hardness.
So what does this all mean for us, practically? Where can we expect to see this physically guaranteed security applied first? Where's the demand highest?
Well, you'll definitely see it in areas demanding the absolute highest levels of security. Think military and government communication, for starters. Securing strategic data there is paramount. Finance is another huge one. Banks, stock exchanges, they're already exploring QKD quite seriously to protect financial transactions and sensitive customer data from sophisticated cyber attacks. We're talking about ensuring the integrity of vast sums of money.
Makes sense. High stakes.
Very high stakes. And increasingly, secure cloud services are experimenting with quantum encryption methods to safeguard sensitive data hosted remotely. Think protecting everything from medical records to proprietary business information, R&D data.
Okay, that covers securing the keys. But what about actually moving a quantum state without physically moving the particle itself? That sounds like the true sci-fi definition of teleportation.
It does, doesn't it? And it is in a specific quantum sense. Quantum teleportation is about transferring a quantum state from one location to another without physically moving the qubit that holds the state. It's not like in Star Trek where a person disappears and reappears elsewhere, unfortunately.
Ah, okay. How does it work then?
Here's the fundamental idea. Alice and Bob first need to share an entangled qubit pair. Let's say they each hold one qubit from this linked pair. Alice then performs a joint measurement on her entangled qubit and the new qubit whose state she wants to teleport to Bob. The result of Alice's measurement is just classical information, a few bits like 0, 0, 0, 1, 10, or 11. She sends this classical result to Bob over a regular classical channel.
Okay, so classical information goes across.
Yes. Finally, Bob, receiving this classical information from Alice, performs a specific operation, a unitary transformation, on his entangled qubit. Which operation he performs depends only on the classical bits Alice sent him. And voila. Bob's qubit is now in the exact same state as the qubit Alice originally wanted to teleport. The state has been transferred.
Wow. And this is significant because it's a way to directly transmit delicate quantum information, maybe bypassing the need to send the fragile physical particle itself across noisy channels.
Precisely.
Yeah.
That's absolutely critical for building future quantum communication networks. It will form a key component, we think, of a future quantum internet. It allows us to transfer quantum information without that original state having to endure a long, noisy journey where it's susceptible to decoherence, to falling apart.
Okay, but this still raises an important question. How do we send these quantum signals or maintain entanglement over truly long distances? Classical repeaters simply copy and boost a signal, but we just established you can't copy quantum information without detection or destruction.
That's the core challenge for distance, you're right. Because quantum information cannot be perfectly copied without disturbance, classical repeaters are completely out. They just wouldn't work. So quantum repeaters are vital. They are needed to overcome signal loss, physicists call it damping, or attenuation, and extend the range of quantum communication beyond, say, a few hundred kilometers in fiber.
So how do they work without copying?
Their operational principle is quite ingenious, actually. It involves generating entangled photon pairs at multiple nodes, or stations, along the transmission path. These entangled states are then stored temporarily, perhaps using quantum memory systems, and then a process called entanglement swapping is used. Essentially, you perform joint measurements at the intermediate nodes that effectively chain the entanglement across the segments, so you end up with entanglement between the start and end points, even though no single photon traveled the whole distance.
Ah, like linking hands in a chain.
That's a decent analogy, yeah. You create these entangled links, segment by segment, and then connect them. Early experimental demonstrations are already showing promising results towards building, eventually, a global quantum communication network this way.
And connecting this to the bigger picture, making it truly global, this is where satellite technology really comes in, isn't it? To expand the reach beyond what fiber can easily do.
Yes, absolutely. Satellite quantum communication is seen as a potential game changer for truly global reach. The Misha satellite, which was launched by China back in 2016, was a real pioneering project in this field. It has successfully demonstrated QKD over immense distances, more than 1,200 kilometers between the satellite and ground stations.
1,200 kilometers.
Indeed. And it even performed quantum teleportation between widely separated ground stations using the satellite as a relay. The potential here is enormous. Satellite-based quantum communication could eventually lead to a global quantum-secured internet, overcoming the limitations of Earth curvature and the significant atmospheric losses that ground-based fiber networks face over very long distances.
That's just astonishing progress, taking something that sounds so theoretical, so futuristic, and actually demonstrating it in space. But despite this amazing potential, what are the significant technological hurdles we still need to clear to make this widespread, make it practical?
Oh, there are quite a few significant challenges still. A really central one is error correction in quantum channels.
Dealing with noise and mistakes.
Exactly. Quantum states, qubits, are incredibly fragile. They're highly susceptible to environmental influences, stray heat, magnetic fields, vibrations. This causes decoherence, where the fragile quantum state essentially loses its quantum properties and falls apart. So quantum error correction, or QEC, is essential. But it's fundamentally different from classical error correction because, again, you can't just copy the qubit to create redundancy.
Because of no cloning.
Right. So researchers are working on incredibly clever error correction codes. Think of them as quantum safety nets. These codes encode the information of a single fragile logical qubit across multiple physical qubits, maybe 7, 9, or even more, using things like the surface code. This redundancy allows you to detect and correct errors caused by decoherence without actually measuring and thus destroying the underlying quantum information. There's also work on inherently robust quantum protocols, like topological QEC.
So it's not just about getting the qubits to exist and talk to each other, but keeping them stable and protecting them from any kind of interference during transmission and storage?
Precisely. And that also leads directly into significant material science challenges.
Finding the right stuff to build these things out of.
Exactly. We need materials and systems that offer high entanglement stability and very long coherence times, keeping that quantum spin going for as long as possible. Key candidates being explored include things like diamond with special impurities called nitrogen vacancy centers, or NV centers. These can actually store stable qubits even at room temperature, which is a huge advantage. Photon-based systems are obviously key for long-distance communication through fiber or free space. Ion traps allow for incredibly precise manipulation and boast very long coherence times, but are complex.
And the superconducting ones.
Right. There's tremendous progress in superconducting qubits, too, the type companies like Google and IBM are using for their quantum computers. They work great, but need extremely low cryogenic temperatures. People are also looking at hybrid systems, combining different approaches, and using nanophotonic structures to improve the efficiency of generating, manipulating, and detecting single photons.
Okay. And then looking beyond the lab, beyond the physics and materials, how do we make this technology scalable? How do we make it ready for widespread use, ready for commercialization?
Yeah, that's the truly huge hurdle, moving from demonstrations to infrastructure. For a large-scale quantum communication network, we're likely looking at a combination of approaches. Fiber-based networks will probably dominate for local and metropolitan connections. Satellite-based systems, building on successes like meshes, seem essential for truly global reach, intercontinental links. And significant advancements in quantum repeater technology are absolutely necessary to bridge those intermediate distances efficiently and connect different types of networks.
And the economic side.
On the economic implications, well, you can imagine the impact of highly secure financial transactions. Entirely new business models could emerge in quantum cryptography and quantum security services. And there's a strong synergy anticipated with quantum computing itself, leading perhaps to future quantum cloud services, where both computation and communication are secured by quantum principles.
But it's not all just tech and economics, right? There must be societal challenges, too.
Oh, definitely. We'll need robust regulatory frameworks for such a powerful technology. Who controls it? How is it deployed? There's a real potential for an unequal distribution of this technology, possibly widening the digital divide between nations or groups who have access and those who don't. And, of course, ethical concerns around privacy and surveillance are always at the forefront with any new communication technology, especially one promising this level of security or potentially new ways to break old security.
So it's a complex picture, but despite these really complex challenges, it sounds like tremendous progress is being made across the board, from making qubits more stable in things like superconducting materials and optical systems to pushing the boundaries of satellite communication way up in space.
Tremendous progress, yes. The research is genuinely pushing the boundaries of what we thought was possible only a decade or two ago. It's rapidly transforming theory into tangible, experimental breakthroughs.
So as we wrap up this deep dive, it feels clear that quantum channels represent a fundamental shift, a really profound change in how we think about transmitting information. They promise, essentially, ultimate security, rooted in the very laws of physics, and potentially far greater efficiency in certain tasks compared to our classical systems. They're truly paving the way for what could be a genuine quantum internet.
Absolutely. And I think the provocative thought for you, the listener, is this. The coming years will be absolutely crucial in determining not if, but when and how this revolutionary technology integrates into our daily lives. It's going to fundamentally change how we transmit information, and that will impact everything from your personal privacy online to the stability of global financial systems. It's a future that's no longer just theoretical. It's rapidly becoming a reality we need to prepare for.
It's an exciting, maybe slightly mind-bending future, isn't it? Thank you for joining us on this quantum deep dive. Remember, this exploration was based on the insightful essay by Jörg O. Schneppat. If you want to learn more and explore his work, you can find information at schneppat.de. Until next time.